Hello, this is Mr. McMurray, and we're back on Chapter 28, Shaping the Earth's Surface, and we're going to be talking a little bit about the hydrologic cycle, otherwise known as the water cycle. It's serious stuff. Some people may think it's all wet, but there we go. All right. So, starting off, about the water. We may hear things about water shortages and stuff like this, and you think, well, how can that be? Because water gets recycled over and over, we can't lose water and so forth. But, bottom line, if you take all the water on Earth, first of all, 97.2% of it is salt water. And salt water, for the most part, is unavailable to us for drinking water. We could evaporate off the water and recondense it and leave the salt water behind, but right now it's just not feasible. If it gets to the point where water starts costing $5 or $6 a gallon, then yes, it may be useful. And there are some places in Africa coast where there's desert all around them that it is worth it for them to produce water from fresh water from salt water. But for the most part, that's unavailable to us. All right. Of the fresh water, 2.14% of it is in the ice caps and in glaciers on mountains and so forth and so on. Now, some say, well, with global warming, at least that will all melt. Well, but a lot of that in Antarctica and the Arctic is just going to go run into the ocean and once again become part of the salt water. So only the freshland glaciers would actually, on top of mountaintops and so forth in the Rockies and up farther north, would actually be useful for this, and it's not going to be a big bump in the water. All right, groundwater underground is 0.5%. Okay, and the surface water is, look at that, 9/1000th of 1%. Okay, and there's about half that is available in the soils, but obviously we can't get that out. Okay, so really of the surface water, which is where originally people had to get all their water from, it's a very small amount of the water that's available. And when we started digging wells where we could get out, that increased it, but we're still less than not even 3/4 of 1% of the water. So there's only a certain amount of water that is available to us. And if we pollute that water to the point where it's not usable or potable, just remember, is the word that means water is drinkable without any health problems or anything, then that's what happens. If we contaminate either the groundwater or these surface waters, then they're no longer usable either. So it's not so much that we're going to run out of water, it's just that we're going to run out of water that we can use and that is clean enough and fresh water enough, not salt water, that we can actually use. Now, because of the water cycle, or hydrologic cycle, but that's just a fancy name, hydro meaning water, so it has to do with hydrology as a study of. So the hydrologic cycle is the cycle of water, and the circle of life. No, that's a different circle, but that's still similar. The idea is that water is over and over recyclable. Okay, for example, water in the oceans becomes fresh again when it evaporates. So we have evaporation from the oceans. Okay, technically we could also have evaporation from ponds and lakes and so forth like that. So there's constantly water being evaporated back up into the air. And if it was ocean water, the good news is now it is fresh water again, because the salt remains back in the ocean, and that's why the oceans continue to get saltier and saltier. Not a great deal because they're so big already, and a little more not going to affect it that much, but technically, yes, they are getting saltier. All right, the water evaporates. Once it comes up in the air, it can condense again, which is condensation, all right, and form clouds and water droplets. And if the water droplets get large enough, then they can fall down as precipitation, or if it's cold, of course, precipitation just means to fall out of. So these are falling out of the sky, liquid falling out of the sky, but gases. It could also, of course, be sleet, hail, snow, whatever, depending on the temperatures. Now, just for the record, if it becomes snow, it's actually called deposition, and it's going straight from water vapor into snowflakes. But we'll just say condensation and then precipitation when it falls back down to the ground. All right. Now, once it falls to the ground, several things can happen. It can soak into the ground. Number 4 here is called infiltration. All right, it can infiltrate or go into the ground. All right, if animals drink it, they can, every time they breathe, respiration, we give off a lot of moisture. If you ever have blown on your glasses, breathe on your glasses to get the water droplets to condense on it so you can wipe them off and clean them. That's basically respiration. Plants do the same thing, but it's done through their leaves, and it's called transpiration. All right, transpiration. All right, but they basically give it back into the air. All right. If it doesn't infiltrate into the ground, since most ground is not flat, it's going to run off and go somewhere else into a pond, river, creek, lake, or possibly the ocean if you're close to the ocean. All right. And so that's pretty much the water cycle, okay? And then the water evaporates back up again, and it continues over and over and over, and it can take different little paths across it, but basically that's the same pattern. Now, if it goes underground, we'll talk about that here in a minute, but that's the basic water cycle. And so water is being recycled over and over again. The water you have in your body may have been part of a dinosaur at one time, or an elephant, or a mosquito, or all various kinds of things, all other living things that have and use water. Now, of this fresh water we have, if we took all the fresh water that's available to us, surface water is only 1.5% of that. Okay, and yet for most of our history, people have used rivers and lakes and so forth for their main source of water. Originally, the Midwest, including this area, if you weren't next to a river, was considered pretty much a desert because there was very little surface water, and therefore people could not settle there. But once we got down to groundwater, water that's stored underground, okay, that is 98.5% of the fresh water that's available. So there is a lot of water, but it's down below the surface. Until they invented windmills and other things to pump them up, it was basically not useful for most people. And so that greatly increased the amount of water available, and we have availed ourselves of that. And even so, our cities are still many facing water shortages. But let's talk about groundwater, because it is a big source of fresh water and where much of our water comes from. All right, so first of all, if something runs off, then obviously that is not going to become groundwater. It just runs over the surface down into the nearest low spot, either a river, lake, pond, whatever. All right, but it's only this water that infiltrates. Now, some of that will stay in the soil, okay? But if it rains more than it can, for example, especially when we get anything over a couple of inches, a lot of that is going to continue to soak down into the ground. All right, and how much of it soaks on depends. Cities increase the amount of runoff. That's why flooding is so much prevalent in cities now, because of pavement, asphalt, parking lots, etc. Many housing developments have to have a little pond that they store all the water coming off their parking lots and so forth. You'll see that more and more. Okay, and so we have greatly increased the impermeable soil, or amount of impermeable roofs on our houses, all these things, water that used to soak in the ground, now it's all running off, and so we have a lot more flooding problems in that. The type of soil is going to affect it. If you have clays, which have the little tiny ones, and then they swell and make like a solid layer, they can stop the water from infiltrating into the ground. Okay, sands, on the other hand, are going to let a lot of the water keep on going down. All right, and so if it continues to go down, we can call this percolation, okay, keeps going there, or we say it permeates. So you could call it permeation, I guess. Okay, percolation or permeation, it continues to pass through the soil particles, okay, if they're big enough to let it go through, and it has time to filter down through. Now, whether we'll let it percolate or not has to do with the porosity of the soil, okay, and porosity has to do with the amount of open spaces or pore space compared to the volume of the soil. So if we do the amount of pore space divided by the total volume of the soil, then that would give us our porosity. So this would be the amount of pore space divided, or volume of volume, perhaps would be a better word there, sorry, volume of the pore space compared to the total volume of the soil. Okay, how much pore spaces are there? Okay, generally the larger the soil particles, we've talked about when we're talking about soils, the bigger the soil particles, the bigger the spaces that allow water to go through, and so we would say they have more porosity. All right. And this is the amount of space possible, one, for letting the surface water go through and sink into the ground where it can be stored. Then once it starts filling up, say there's a solid layer down here that is impermeable, all right, it can't go down anymore, then it starts filling up these spaces, okay? And so all these spaces in here would be completely filled with water. Okay, and so if you have lots of pore spaces, then you're going to have a lot more space available for this water to be stored in there, and it can hold more water. Porosity then has to do with how much space there's. Now, there's something similar to that we talked about is permeability. Okay, permeability has to do with how well does it let things flow through it, okay, or the degree to which a porous material is allowed to flow through it. So does it let water through it? Now, for example, we said clay particles are very small, and so technically there's a lot of pore spaces between those particles, but they're very small pore spaces, and especially if it starts to swell up any, it shuts those pore spaces off. And so clays technically have high porosity. Okay, there's a lot of pore space in there, but they're so small it's hard for the water to go through, so they have very low permeability. Okay, because water actually has a hard time going through. Okay, sand, on the other hand, up here, like we talked about, sand has high porosity, but it also has high permeability because the spaces are big enough that they allow stuff to flow through easily. All right, and so those are very important. Now, if you're looking at the water table, all right, water will continue to go down through these layers. Okay, they're going to keep going down and down until they hit some type of impermeable layer. Okay, impermeable means it will not let it go through, and it can't go any farther. Otherwise, it just keep on going down there till it hits the mantle and then start turning into steam or something, which can happen in geothermal energy. But anyhow, impermeability, it hits it. Now, once it can't go any farther, then the water starts backing up and filling in all the pore spaces. Okay, the boundary, kind of like the top of the water-filled pore spaces, if you will, is called the water table. People talk about how deep it is. The water table is 300 feet deep. Then that means you have to drill 300 feet deep before you can reach any water. And that tells you how deep your well would have to go to get in there and pull water out of it. Okay? And the water table then is the dividing line. Down here we would say that the rock layer or sand layer, whatever it is saturated. Okay, and up here it would be unsaturated. The water is still moving down. Now, keep in mind, these soil particles would still retain some of that soil moisture. It'd still keep around the soil particles, but there's still air spaces and the water can still continue to go down. Saturated means all the spaces are filled up with water, okay? And so the water table is the dividing line between that, or marks the top of the groundwater. Now, the stuff down here, we need to notice are two things. The rock layer is known as the aquifer, and this is the rock or soil layer that contains the water. All right, and so the aquifer is actually the stuff that the groundwater is the actual water. Okay, so sometimes people talk about pumping out the aquifer. We don't pump out the aquifer. That's the rock or soil layer that contains the water. The actual water in that is the groundwater. So we pump out the groundwater from the aquifer. Okay, but the aquifer would still be there even after we pump out the water. All right, this picture demonstrates what we're talking about. Here you have waters come down, there's soil moisture, but there's air spaces between the particles here. Once you get down below the water table here, then it's completely saturated. There's water in all those zone here. Now, and here, if we have a water table, if the surface dips down below the water table, then there will be streams, lakes, ponds, things like that will be formed. Okay, and the water will come out at the surface. Okay, but notice that if that's normal water tables up here, then yes, it will feed into the stream. But in a drought, when it dries up, the water table drops. Water's getting pulled out of it, but no water is being added back to it, and these places will dry up.